ladies and gentlemen. Hello, everyone. This is Alice in Beijing. I'm so glad to meet you again at ICANX Talks. Every Friday, we have this wonderful event to connect the world and the universe. We try to invite the top scientists from the worldwide and to deliver their talks and their latest results, to see how this high tech changes the world. So this ICANX talks was since April, so now it's already run 8 times. This was 8 times. And this is one part of the PKU's X license. This was an online class too. So this talk is very, very popular. Every week we have more than 300,000 audience, worldwide. So we are so proud of that. So if you don't know more about ICANX yet, please follow us on Twitter. Please find the video replay on YouTube. And if you have some questions, suggestions, please take this ICANX online survey. So today is a big day for ICANX talk. Today is also a big day for mine. For me, why? Because today is mine day. Mine is young scientist lectures. As mine is an event we run for several years. This was sponsored by a journal was named Microprocessor and Nano Engineering. So every year we pick up the wonderful, outstanding young scientists worldwide. And today is a big show for all these young scientists, young stars. So yeah, this we have already 4 of them to present on this stage. Now the first welcome is Professor Cunjiang Yu. Cunjiang Yu was from Houston. I gave his nickname is Rocky from Houston. We all know that Rocky, flew to the sky, space is from Houston. Cunjiang was like this. Professor Yu was really young, but is quite famous. He grew up so fast, get a lot of nice work and many recognized technical contributions in this area, especially in the Rubbery electronics. He established in his lab and his group in the last few years. He's get very well known in this world. So Cunjiang, are you ready? Yeah. Cunjiang, please turn on your video and turn on your cameras. Yeah, now is your time. Yeah, please share with us. Yeah, so Cunjiang will give us a talk for the Rubbery electronics. Yeah, so the word is yours. Cunjiang, please.
Especially those challenges are related to or associated with health and joy of living. So in particularly, we're being interested to creating technologies or implementing devices that to understand the human body and also biology and also to provide remedy solutions. We are also interested into creating or implementing smartness and safety into robotics or machines. So we believe that human and robotics or machines will team together and the boundary between them will become very blurry in the future. So specifically, we're utilizing soft electronics to solving these great challenges. So on one hand, human is full of organs, tissues that are mechanically soft, while conventional electronics, like silicon wafer technologies, they are rigid. So to bridge electronics with human, future electronics need to be also mechanically soft, similar as human body. On the other hand, soft electronics can also provide machines or robotics certain capabilities or functions to allow them interacting in and responding in the complex environment. So my group in the past few years really covers the fundamental and application aspect of soft electronics. So particularly, we're a device research group, and we're design new materials with tailored properties for devices, and then we manufacture these materials. And of course, manufacturing is two-level manufacturing those materials, gearable manufacturing, and also manufacturing devices, manufacturing technologies to allow us to build in the devices. Now, we utilize the materials and manufacturing technologies to creating devices for medical and for machines. So this is generally what my group has been covering. So soft electronics is such an example that we have top-down research of solving the specific application needs by seamlessly to merging biology or human body with future electronics. And we really come out with material solution and building devices to solving this great challenge. So to start with, so look at the silicon wafer technologies, conventional electronics. So instead of look at the electrical functions, but we look into the materials we're associated with for this device, which includes semiconductors, conductor materials, dielectric material, and also substrate of silicon wafer, for example. And we look into the fundamental material properties as a curve of strength. So we can see, this metal is a ductile material, and also a lot of semiconductor materials or the dielectric materials, ceramics or inorganics, they are actually fairly brittle. So we can see none of these materials behave like a piece of rubber. They are not stretchy. So in the past or so, there's an emerging field we call the stretchable electronics. So now the electronics can be stretchable, but these materials are not stretchable. And this has been so much development in for healthcare, for portable electronics, for energy, for display, etc. So how we utilize unstretchable material to create stretchable electronics? So this is really coming from a simple principle that probably that's what we call the architectural engineering over here. So as example, a piece of stainless steel, which is not a mechanical stretch. Now, if you coil them up, you can make a spring structures, and now you can stretch a spring. So you can see same material, but based on different architecture, we utilize this engineering concept, and by applying to our engineering designs, we actually can create, for example, wrinkle structures by harnessing a ring film with the elastic structure. So it's very beautiful that harness modern and we actually can create a very uniform waves depending on the thickness of this and also a difference between the models. So once we create these wrinkle structures, you apply mechanical stretch. And instead of directly fracture a rigid piece of material or fail those materials, but now actually you're changing or modeling waves or amplitude of these wave structures. So now you know how to create different types of stretchable electronics, where the electronics are built based on these rigid films. So it's very nice. We can create these out-of-plane structures, then we can make a device stretchable. So this is talking about the direction. What about implant? So in also similarly, you can create open match structures. So now similarly, when you apply mechanical stretch, you're opening these meshes, and instead of directly thinner this material, but now you're changing the geometry to accommodate the mechanical stretch. So the implant is also a very powerful technique to creating many, many stretchable electronics. And in the field of stretchable electronics, this architectural engineering has been really dominant to creating a lot of devices for many applications. But one thing I want to mention, especially many people and many advances has been really has been existing in this field, including my group and also a lot of many pioneers. For example, John Rogers, Yonggang Huang has been creating this technology out of plane in-plane structures, and this is out of plane structure designs is also my PhD thesis. And later on, I work with John Rogers and creating this implant structure designs for many stretchable electronic device development. So it's been very successful and it's being proven to be working very well. But one thing is when we look into the problem, especially when we utilize these devices, try to merging with biology, especially for organs or tissues, problem comes. So for example, if we look at the existing stretchable electronics based on architectural engineering design, when we use our hand to stretching a spring structure or deform it, so we can feel the mechanical stretchability. But the mechanical stretchability is at a structure level or macroscopic level. So now, once we utilize this technology or architecture engineering to interface with organs, tissues. So for example, a heart over here. So heart is made of hard tissues with different cardiac cells. So you can see those organ tissues, actually they mechanically deformable, but also those cells, actually there are no rigid components involved. So now, especially once we try to utilize this architecture engineering principle and bridge or interface with those tissues, cells, the tissue and the cell will not be able to feel the macroscopic mechanical stretchability. They can only feel the microscopic or local material stiffness. So this has become a challenge. So the question is, can we have a way to creating electronics that have mechanical stretchability at both macroscopic level and also microscopic level? So this is a challenging question to solve. So in the past few years, we really have been thinking and we try to creating a fundamentally different way of creating electronics, which we call the rubber electronics. Rubber electronics is type of electronics that completely made out of rubber materials. So we want to utilize materials following this red strength curve. And this red strength curve can mechanically stretch and also release back and forth and without feel this material. So what we think is that if we have all these electronic materials with this mechanical property, and then we can immediately probably can turning a piece of glove we're wearing in the laboratory now to make a piece of integrated circuits. So with this technology, then actually immediately many positive outcomes or impacts were bring in. For example, they really bring new electronics, new optoelectronics, new design principles, new bioelectronic platforms, new machine interface technologies, etc. And one of the most striking advances is it really solving this great challenge of seamless integration between electronics and biology, because now all the electronics are very similar to the organs, to the tissues, to the cells in terms of their mechanical property, mechanical deformable. So to creating this type of rubber electronics or bioelectronic platform, we actually aggressively associated with a lot of electronics, such as active metrics for readout circuits, analog digital circuits, sensors. So to create these circuits, components, sensors, so the fundamental units to creating these devices is a transistor. Now, to make a transistor, we also know transistor associated with at least 3 key materials. So one is the semiconductor, one is the conductor, one is dielectric. So we really want to utilize this rubbery version of all these materials in this regime of the strength curve to creating rubber electronics. So as I mentioned, there are so much advances in the past few decades in terms of material development. So now let's see what the community has been offered us. So looking into the conductors, so making a conductor be stretchable that have the similar mechanical property, use all the soft materials, you can immediately find out people has been researching of 0D of the nanoparticles, 1D nanowire or nanotubes, 2D of nanoflakes, and mixing and creating these composite structures. or even these days, talking about these organic conductors, they can tailor their mechanical property and they can make it very soft like a piece of rubber. So it's been great. There's a lot of options. So the specific material, what we have been creating and utilizing is we're using nanowire materials. Especially we're using silver nanowire materials over here for our devices, which I'm gonna describe in the next few slides. The reason we're utilizing this nanowire material is because it's very high aspect ratio, and that we'll only need a very small amount of material to allow the percolation working. And also for these materials, we actually care about the surface functions that we can chemically modify to allow the match between the semiconductor and the conductors to allow the creating the ohmic contacts instead of Schottky barriers. So basically, the message is that there are tons of options for conductors. Now let's look at the dielectric material. So dielectric material, for example, elastomers, they're electrically insulating materials, or a lot of ionic gels, they're also mechanically stretchy, but they're also has been proven to be utilized for dielectric materials. Looks like this is also not a problem. So what about semiconductor? So when we start looking at this problem back in 4 or 5 years ago, there no such a material exists. So the first challenge problem is that can we create a rubbery, stretchable semiconductor materials? So we have been working on and come out different types of options, but one option eventually worked it out is we're actually utilize these polysilicon nanomaterials, and especially in the way of the nanofiber structures, and then we can create an elastomer matrix as the double penetrated composites for the nanofiber structures. And when you mechanically stretch it, even in some places are losing their junctions, but still those wires actually have certain connections to allow the carrier to transport through the whole network. So based on this design principle, we found a way to creating this material. We utilize the solution phase of material by inducing the cooling and resulting in this homogeneous self-assembly approach to creating the nanofiber structures. And then we can introduce this rubber matrix network. And eventually we can utilize this material to creating, for example, a solidified rubber material, which is looks like, as I showed over here, the microscopic structures. The bright color represents this nanofiber structures. So you can see we can stretch 10%, 30%, 50%. And we do observe some of the disconnection size for these nanofiber structures. But overall, based on our device evaluation, this actually, or those materials still function as a semiconductor. And macroscopically, this is a piece of rubber material. So you can stretch, you can twist. So one thing I want to also highlight over here is we're creating this type of rubbery semiconductor material is we really want to eventually make it integrated electronics. So now the most important thing for utilize this material is you allow the scalable manufacturing. So based on solution phase of the precursors, we actually allowing all the coding, printing technologies to allow us to creating integrated electronics. So indeed, this is our first generation of the materials. So because of time, I will skip the details, which you probably can find more in this literature. And later on, we actually also improving these materials and to creating more and more scalable manufacturing material. For example, roll-to-roll manufacturing by harnessing the water-air interface and also the phase separation, we can creating rubber semiconductor film in the roll-to-roll processable manner. And also those devices can be roll-to-roll manufactured. So it means now we have a way to creating these rubbery semiconductors. So now we have all the material options. So then the first test-bed device is a transistor, a basic unit or building block for the electronics. So for those who are not very familiar with the transistor, so transistor is an electronic device that been very similar to a mechanical device that everyone is very familiar with, like water faucet. So water faucet is using the back of the gate mechanical to modulate or changing the source and the drain of the water current. So is you're applying the gate voltage to the gate on the G on the gate end, and then to modulate the source and drain current flow through the S and D terminals. So now the good thing is that different from traditional silicon-based technologies, we all based on rubber materials. So these rubber materials we can allow to creating a rubber transistor. Eventually, we can mechanically stretch. So we, based on this device architecture and also the material associated with, we do find out this device working very well. So this is utilize our first generation of those semiconductor materials. And we do see applying a few volts of the gate voltage, we have the few orders of magnitude modulation of the source and drain current. And most strikingly is that these devices, you can mechanically stretching, for example, 10% along the channel length direction, along source and drain, or by 30, 50%. Even you stretch perpendicular to the channel length direction by also 50%. Those devices working very well. But we do see some of the current changes. Current level, for example, the source and drain current level have certain differences. So to evaluate those device performance, one of the very critical measure of this device is looking into the field effect mobility. All right, so based on the capacitor model of the transistors working as a so we can write the equation of IDS is a factor of the geometry of the transistor and also the gated capacitor times the mobility, which is denotes the how fast the carriers move under a unified electrical field between the source and the drain, and also the gate voltage by this second order. And we can rewrite this equation, and instead of using the VG square, but now we actually can have the VG, which we plot in this blue curve right here. And this blue curve represents the VG as a relationship to the square root of IDS, which is very important because now we can have direct information to find out how the gate modulation of the IDS. But one thing also find out is if you look at this equation, and this equation, the square root term over here is actually the slope of this square root IDS versus the VG. So now, based on this slope, we can calculate from the curve, we can also derive the field effect mobility. So based on this field effect mobility, we find out that this material actually, or this device, even after stretching by 50%, this device working very well as a transistor. But we do see the mobility have the 40 to 50% of decrease, which is what we expected, because once you mechanically stretching these nanofiber structures, and there are actually disconnection sites, and eventually reduce the transport efficiency, thus the field effect mobility decrease to somehow. So, and also I want to mention here, this is our first generation materials. So the mobility is in the range of 1 centimeter square per volt seconds. It's good, but it's not great for integrated electronics. Eventually, we want to converting a piece of rubber to integrated circuits. So now we want the transistor working very high performance. So now the caliber is how can you make the device being very high performance or creating this high mobility materials. So indeed, this is our second generation material, which we call the high mobility rubbery semiconductors. Instead of this two material system, but now we're incorporating the third material. The third material we incorporated specifically over here is we're utilizing metallic carbon nanotube, and also has a very low aspect ratio. This is on purpose because we want this a very low aspect ratio does not short the channel of the transistors. And also we utilize this metallic carbon nanotube because the working function match very well of the HOMO level of the polysilicon nanofiber to allow the carrier to easily flow through. So we come out of material fabrication and also optimization approach based on looking into the drain current and also the off ratio, look into the mobility. The details, because of time, I will skip, but you can find out in the reference listed below over here. And we find out that if you put a 0.5 weight percent of metallic carbon nanotube in the composites, you actually maximize this material with the fairly high mobility and also high off ratio. So especially we boost the mobility from 1 to 10 by introducing this metallic carbon nanotube. So also we're not just making one transistor, but we're making integrated array of devices. So this is a 8x8 array, or based on the printing process. And this is the mobility map, fairly uniform device mobility. And everything is made of piece of rubber, so you can mechanically stretching, bending, or kind of mechanical deformation. The device does not fail after many, many cycles of the operation. So we have the technology and the materials to creating this rubbery transistor integrated electronics. But if you look at our computer and also the integrated circuit chips, so they are actually working digitized or talking about 0-1 operations. So we also creating a logic gates, which, for example, you have the inverter input 1, you generate 0, and also other gates like NAND gates and NOR gates. So the message here I want to tell you is, based on our rubbery transistor technologies, and we can create a fully rubbery logic gates. And those logic gates, even under mechanical stretching, they can preserve their logic functions. So the details also can find out in the paper over here. So with this logic gates, of course, it's not a fully very hierarchy complicated integrated circuits yet. That's something we still been working on. Hopefully we're gonna come out integration level up to thousands, even more. So now we have those transistor and integrated electronic technologies. So some of the things immediately we think this technology can be really helping solving the challenge is, for example, smart skin. So smart skin is a great technology, but the smart skin, especially when the sensing nodes significantly increase, then you're facing a lot of challenges. So for example, if you have tens, hundreds, or even thousands of the channels or sensing nodes, so the crosstalk, the wiring is really become a problem. And what we have been thinking is, can we create a smart skin and utilize our transistor active technologies to solve this challenge? Because this technology is working similar like a display we're being utilizing. And particularly we're creating a tactile sensor skin based on fully rubber technology, utilize the active matrix of the electronics. So this is the device architecture I want to show here. And you can see the sensor components over here is a pressure sensitive rubber, and it's mechanic deformable, a piece of rubber. And also the electronics part is all based on rubber electronics. So now putting this together, and you can see now we're pretty much creating a touch skin, interactive skin that can resolve the tactile pressure. So the working principle for this device is that you apply the mechanical pressure for each channel of the device. Actually, this will induce a change of the voltage across the shunt resistor. And by scanning the bit and word line of this voltage, then we can back calculate the tactile or the pressure applied on the skin. So now you can have the multiple channels of the skin active matrix technologies. And again, everything is made of piece of rubber, so you can deform, and also this device can resolve the pressures applied. So based on this technology, immediately this can really solving or implementing this smart skins, e-skins for many, many applications, for robotics, for artificial or skin prosthetics. So now for skin prosthetics, one thing I also want to mention here is, especially say we're touching our arm, all right? So once you touch your skin, you actually can feel it. So what's going on? So the mechanism is really your skin have many mechanical receptors. So those mechanical receptors, upon the mechanical stimulation, they generate those receptor potentials. Those receptor potentials actually will activate those biological synapses and transmit through the nerve fibers and generate those post-synaptic potentials and eventually to your brain. So now your brain can feel it. So one attribute I want to also mention for this synapse or neuron functions is this actually also those neuron functions, those neuron synapses are mechanic deformable. Even those exist in our tissues, in the spinal cord, there can be mechanics stretched by more than 30 or even more, 30% or more. So I can use one extreme case of earthworm. So earthworm, they can extend their body by a few times. Their neuron synapse also can allow this large mechanical deformation. So now the question is that, can we create very elastic neuron functions and build into our skin devices? So that's what the core technology behind it is we creating elastic synaptic devices that allow the neuron function, memory capabilities to exist in these devices. So because of time, I will skip the details, but what I want to emphasize here is based on similar like a transistor architectures, we can creating elastic stretchable neurologically synaptic devices, and after mechanical stretching, they still can preserve this memory effect, these neuron functions. And with this technology, we actually can creating a smart skin. So for example, our smart skin behave like our natural skin. The skin we build in this rubber elastic mechanoreceptors. So now once we mechanically press, interacting with our skin, so we generate those potentials. Those potential actually will trigger this synaptic transistors, and eventually they're going to generate arrays depending on number of sensing nodes you have or the mechanoreceptor you're interacting. So now you generate arrays of post-synaptic current, or you resolving this post-synaptic potential. So now you can mapping out this post-synaptic potential, then you can trigger in these biological neurons. So this is a device. We have those artificial synaptic transistor devices, and also with the mechanoreceptor units, or based on rubber devices, and we can resolving this post-synaptic potential. And also we have been working really utilize this post-synaptic potential to triggering these biological neurons. So that way, eventually you have the skin prosthetic, you're interacting with the artificial skin, your brain can feel it. So this is something we have been working. And with this technology, it's also, we feel like probably also change the way how the robotics behaves. Traditionally, robotics, the operation or based on the control or the command by the operator. So now what we have been thinking is eventually those robotics become very smart. So we have been really asking ourselves, can we create robotics that allow the robotics to think like our human or animals, or even they have a mindset like us? So how to achieve these capabilities? So it looks like with the neurological function integrated skins, we can implement this soft neural robots. Of course, this is a first strike along this direction. We really have been implementing this neurological neural robots with smart skin technologies and use the neural decoded signal based on the robotic memory. And we can actually give the command by interacting without giving any command, but the robotics, once interacting with external environment, they can memorize and they can perform their, for example, cloning motions. So this is one example of, based on the interaction, like a tapping modes of the specific neurological decoded signals, then they can allow the robot to automatically to walking or changing angles or some other motion behaviors. So the detail of the neural decoded signals, this also appear in the literature in the end of the slides. So I already showed a couple of examples of creating these engineering devices using our Rubbery electronic technologies. So now I also, going back, because we really want to seamless integration with the human body, with the electronics. So this is one example which we called Rubbery bioelectronics, utilize the epicardial patch as example. So this epicardial patch, we actually allow to creating a Rubbery bioelectronics patch and sitting on a beating heart. And also we can allow special temporal mapping of the electrocardiogram signals. And this is the real-time monitoring of this R peak over here. And the cardiologists become very excited because the device is so soft, they can concurrently deform with the heart, and also they can simultaneously to mapping out the ECG signals. and not just the mapping of the signals, but also give the detailed information of how the signal propagating along different directions to identify the arrhythmia or tracking the arrhythmia behaviors. So now we also, for this Rubbery bioelectronic patch, we also integrate some other electronic sensing functions and even therapeutic devices to creating this whole functional bioelectronic patch for heart behavior monitoring, pacing, and also therapeutic capabilities. So with that, I think my time is pretty much over there, and I would like to quickly summarize my talk by providing a roadmap. So this roadmap is really placed in contact with what a last century has been strikingly advanced the whole world, which talk about back in the 40s with realize the importance of piece of the black rock silicon now need to the late 40s of creating a nonlinear electronic device called a transistor. So now later on, early 60s, creating this circuit devices from Texas Instrument, and then later on have the large scale integration or very large, even ultra large scale, ultra large scale integration. So for our rubber electronics, so over the few years, we have been developing rubbery semiconductor materials and keep improving this material to allow us to give a very high performance of those electronics, transistors, and to creating or allow this transistor device working, and also we creating circuit functions for the rubbery electronics. And of course, we also been working on the integrated electronics. The level of integration is not comparable with the VOSR yet, but this is some of the direction we have been working on. But simultaneously, we also have been immediately utilize our rubber electronics for a lot of applications for human and for machines. So with that, I would like to stop here, but I would like to acknowledge the work being done by my group. And especially I want to highlight here two alumni from my group, Hei-Jin Kim and also Kyusun Sim. So they're now professors some in Korea. And also a few other people I highlighted here, they're taking the lead of the rubber electronics in my group. And the animal experiment has been really working with fantastic collaborators at the Baylor College of Medicine of Dr. Taylor and also University of Chicago of Dr. O. And finally, I would like to acknowledge the funding supporter to allow us to carry out this work. And thank you very much.
Okay, great. Cunjiang, as always, your talk is fantastic. So yeah, there are a few questions was come out. So first is yeah, wonderful talk, Professor Yu. Yeah, is want to ask you for the questions for the long-term stability of rubber electronics, and yeah, how about the temperature and humidity, the effect on these materials? Clear?
This is a great question. So the long-term stability, it's a very challenging problem. So we have been really working on this problem. So I can tell you, based on our so far the experiment results, we didn't do any aging tests, but we have been creating this transistor device and stay there for more than 2 years. It's still working very well. And there's a reason behind it why this material system or the device is more stable. It's because the material actually compared with pristine organic materials, now we have this rubber matrix is really helping actually preventing this interaction with the moisture environment or other things. So this is a good thing about it. And temperature do actually change this carrier concentration, like the silicon technologies. This device is working fairly well under about 100 degrees, but over 100 degrees, you're going to cause a problem. Material going to degrade.
Okay, great. So the second question is, can you compare your rubber electronics with silicon or some latest results from the silicon carbon nanotube based electronics or other soft electronics? Can you compare with your technology with them?
Sure, this is a great question. So silicon technology, so single crystal silicon has a mobility of 1500 centimeters square per volt seconds. And the carbon nanotubes, even graphene, those materials can over 10,000. So our rubber semiconductor, so far what we have been achieving is about 10. So you can see, we're still very, still neck behind. So that's something we keep improving. So in terms of the flexible electronics, I think rubber electronics is really good in terms of mechanical properties. So depending on your application, if you really want to make a gigahertz operation of the computer chips, I don't think rubber electronics can be immediately to replace this technology. But for some of the technologies, for frequent requirements not that aggressive, then for example, some of the bioelectronics, interface electronics, reading out circuits for the bioelectronics. So this rubber electronics could have certain advantages.
Okay, I have a question following this. So, can you tell us something for the fabrication for your rubber electronics? Is you can also use for the software electronics, the printing and all these kind of technologies is the same?
Yes. So the material we're so far been working on is primarily based on all kind of printing or spin coating process. So make them being compatible with conventional microfabrication. And even one thing I want to also highlight here is the rubber electronics is a microelectronics. We're also using a very low cost, but for large area, which called a 3D printing or some other screen printing technology. So this looks like they are very versatile to work with different types of traditional microfabrication and also this screening, those emerging printing technologies.
Okay, here is another question from Professor Yu. How about the adaptability between different materials and different layers? I think for several layers, so the adaptability.
So this material actually it's a very thin material, so they actually can adapt very well in terms of conformal coating. So yeah, so far we didn't have a very deep trenches involved, so it looks like it's okay. But I think if it's very deep trenches, we have to be looking very carefully.
Okay, great. So the last question is for the roadmap. You give the roadmap for your rubber electronics. So here is what's the big advantage for this technology? What's the target market?
So this is also a great question. I think the market could be really from different sector of the industry. For example, the interactive displays, touch panels, the smart suits, and even a lot of bioelectronics. I think the application is very broad.
Okay, great, Cunjiang. Yeah. Okay, thank you very much, and thank you for your wonderful talk, for your great, question answers. Yeah. Okay. Yeah, I will give you a certification as usual. Because on ICANX talks we invited the most famous professor in the field. Today is really special. We want to deliver this certification to Cunjiang. Can you switch back to Cunjiang? Yeah, Cunjiang. Yeah. So this is for you, the certification for Connect the World and Universe in ICANX talks. Thank you so much.
Thank you.